This is Chapter 12, Part 2 from your Essentials of Radiographic Physics and Imaging book. This begins on page 159 of your text, and this whole portion is talking about radiographic grids, how they're constructed, what their purpose is, some math associated with that, and some errors that can come about as a result of using grids. So we begin on page 159, and the first thing that they start to talk about is the radiographic grid. That picture is actually on page 160, but before we start talking about that, recognize that the radiographic grid came about in 1913 when Gustav Bucke actually invented that. His original grid pattern was a crosshatched grid. And what that basically meant was that the lead lines ran in two directions at 90-degree angles to each other. And we'll look at that in just a few minutes. Gustav Bucke was actually a radiologist, which kind of makes sense if you think about it. The only people that would really be interested in improving the overall quality of the image and eliminating scatter from reaching your image receptor would either be a radiologist or technologist. So Gustav was actually a radiologist that came up with this radiographic grid, the original grid pattern. And then basically in 1920, Hollis Potter came along and improved on the original grid design. He also was a radiologist, and he ended up removing one set of the grid lines so that the grid lines only ran in one direction. And he also added motion to that grid so that you could blur out the grid lines that were being seen on the radiographic images. He figured out those two things would also help improve the quality of the image that was seen. When they start off talking about a radiographic grid, basically on page 160, when they show you this, they show you the composition of a grid. So you've got the image receptor down here underneath the grid. Basically, your patient would be above, so the grid is placed between the patient and the image receptor. So a grid has very thin lead strips. Okay, so these are representing the lead strips. Remember, lead is atomic number 82. So those are the lead strips. And then in between, there is a radiolucent inner space. Typically, it's made of aluminum, which is atomic number 13. So it allows, with the radiolucent inner space, it allows photons to pass through, whereas the radiopaque strips ideally would capture any scattered radiation. So when you have scatter created in the patient, ideally you have this scattered photon that's coming at an angle, and ideally it gets absorbed in the lead strip. But realize that depending on the grid ratio, which we'll talk about a little bit later, some scattered photons can still make it through and strike the image receptor. So a grid will not eliminate all scatter from striking your IR, but it does help to improve and eliminate some of the scatter from reaching the image receptor. In theory, the transmitted photons would come right down and make it through the radiolucent inner space, but again, if there happened to be a transmitted photon that came down right into the radiopaque strip, it would absorb that transmitted photon, and the grid has no idea the difference between a transmitted or a scattered photon. So whatever passes in its path, it will absorb that radiation. So in theory, the transmitted photons strike the IR, and the the scattered photons from Compton scatter created in the patient would be absorbed. When we look at the construction of a grid, again, they have very thin lead strips or lines. And when I say very thin, realize that when we're talking about this, typically you would have 103 lead lines in 1 inch, or you would have approximately 40 lead lines in 1 centimeter. Okay, so extremely thin lead strips are in this grid. And that's referencing the grid frequency, which we'll talk about in 1 second. So when they talk about thin lead strips or lines of lead, that is the radiopaque material in a grid. And then again, you have radiolucent interspace material that separates the lead lines. And typically that is made of aluminum, which is atomic number 13. Your lead lines and your interspace material are then all covered by an aluminum front and back panel that also allows radiation to pass through. And remember that this grid is placed beyond the patient, but in front of your image receptor. And ideally, the conditions that necessitate using a grid would be if the part exceeds 10 centimeters in thickness and your operating KVP is above 60. So if those conditions exist where the part is thicker than 10 centimeters, which is about 4 inches, or your KVP is 60 or above, you should be utilizing a grid to help eliminate scatter radiation from reaching the image receptor. They also reference that the grid can be described by its grid frequency and its grid ratio. So when we talk about the grid frequency, it literally is the number of lead lines per unit length in either inches or centimeters. So the most common grid frequency is typically 40 lines per centimeter or 103 lines per inch. Those are the most common grid frequencies that we see. The grid ratio is mathematically a formula that is the ratio of the height of the lead strip divided by the distance between them, or the interspace. So you can see kind of down here, grid ratio is equivalent to the height of that lead strip. How tall is it? Divided by the interspace that divides them. That would give you your grid ratio. And we'll talk about, typically grid ratios usually range from 4:1 to 16:1. The lower the grid ratio, it means that there's less lead content. It also means that there is a wider interspace to allow more photons to pass through. So it does not clean up scatter as well as a high grid ratio. Now, a high grid ratio like 12:1, 16:1, there's more lead content. Your interspace is narrower, so it cleans up scatter much better. The problem is that you have to be more precise in your position. So there's more wiggle room with a low grid ratio, but it also doesn't clean up scatter as well. Higher grid ratio would clean up scatter better, but there's less wiggle room for error. Okay. They give an example on page 160 to calculate grid ratio, and they ask what would the grid ratio be if the lead strips were 3.2 millimeters high, separated by a 0.2 millimeter interspace. So you literally would take 3.2 divided by 0.2, which would give you 16. So that would be a 16:1 grid ratio. That's the simplest way to calculate grid ratio. Most of the time when we utilize grids, that information is all contained on a label on the front side of the grid, and we'll talk about that in a little bit. As far as the grid pattern, there are two types of grid patterns. They can either be a linear pattern where the lines run in one direction, or it can be cross-hatched where the lead lines run at right angles to each other. So when we're talking about the original grid invented by Gustav Bucke in 1913, this would be an example of that. This is what Gustav Bucke came up with, where the lead lines run at right angles to each other in a cross-hatched or a grid pattern. Okay, this cross-hatched grid. And then in 1920, Hollis Potter came along and realized that if you remove that second set of lead strips and you only have the lead strips running in one direction, you get, you can manipulate the grid and the positioning a little bit better because you're not always going to be running into the lead lines. And he also realized that if you removed one set and added motion to it, you could blur out the grid lines that were left so that they wouldn't show as artifact on the final image or radiograph. With this, it produced a waffle pattern on all the images that were created. So they would have to dictate that a grid was used that cast that waffle pattern on there, and it tended to obscure anatomy. When Potter came along and removed one set, it definitely improved the artifact factor, and it improved the overall image quality. So this is the more current pattern that we use, is a linear pattern where the lead lines only run in one direction. This also allows you to angle the central ray, because you could angle along the long axis of the grid lines, or the lead lines in the grid. You could angle cephalic and caudal. With this one, you could not angle in any direction because you would force some of the photons into the lead lines. Okay, so that references your grid pattern, either crosshatched or linear. When they talk about the grid focus, it's basically the orientation of the lead lines to each other. And again, we have two types of grid focus. We either have non-focused or a parallel grid. Okay, so in this one, they're non-focused, or the strips run parallel to each other, meaning these lines would never intersect if we continued them on. They would never run into one another because they're parallel to each other. So you can have a parallel or non-focused grid. And then this one is considered a focused grid. And with this, the lead lines are angled so that it matches the divergence of the primary beam. Okay, so a focused grid is typically what we use so that the lead lines match the divergence of the beam, which allows us better scatter cleanup on our image. I'm not going to tell you that we never use a parallel grid, but grids that are found in the table and in the bucky of a radiographic suite are typically focused grids that we use. The advantage of that is it allows more transmitted photons to reach the IR, and it's better at scatter cleanup than a parallel grid. Okay, so we have two patterns. Our patterns are linear or crosshatch, and we also have two focuses. We have a parallel grid or non-focused grid and a focused grid. When they talk about the grid focus or a focused grid, again, it allows more transmitted photons to reach the IR. Picture A here represents a parallel grid. Okay, and what you can see is when the primary beam is sent out, all of these photons on the edge of the primary beam get absorbed in the lead lines, because once it diverges to a certain point, it intersects with the lead lines, so that you end up with exposure right here, but on the edges you have no exposure because all those photons were absorbed, transmitted or scattered. The grid does not know the difference. When you have a focused grid that matches the divergence of the beam, it allows more transmitted photons to come through and actually reach your image receptor, which gives you better overall exposure. So a focused grid is ideal for what we do, especially in the wall or the table bucky. Now, how do they determine the angle of the focused grid's lead lines? It's determined by what's called a convergent point or the convergent line, and this is also found on page 162. The convergent point or the convergent line helps determine the focal distance of a focused grid, meaning that you would have to use a focused grid at a specific range of SIDs in order for it to match the primary beam's divergence. If you don't utilize the grid within that focal distance, then you will exhibit what's called grid cutoff. Okay, so the focal distance is the distance between the grid and the convergent line or convergent point. So we said, again, just to point out, with a parallel grid, these lines would never ever intersect. But with a focused grid, these lines end up intersecting or meeting at a specific point. If you were to continue the line up, they would all intersect at what's called a convergent point. And if you did that from both ends of the grid, you would have 2 points, one at one end of the grid, one at the other. And if you connected those 2 points, you would end up with the convergent line, meaning that's the point where they all intersect, and you connect that, you end up with a convergent line. Now, how does that play a part in determining our focal distance? Because when you have that convergent line or that convergent point, what it tells you is that you can determine the focal range, meaning that if you were in this range slightly below the convergent line or point and slightly above, that you are still going to match the divergence of the beam, making this grid good to utilize, or meaning that it would still allow transmitted photons through if you stay within this focal range. So the focal range is the recommended range of SIDs that can be used with a focused grid. And it's determined because someone has taken what the angle of these lead lines are, determined where they intersect, which gives us our convergent point or convergent line, because you're really connecting both of them. And they've determined that if you stay within the range where it's a little below to a little above that, whatever that distance is, then the photons in the primary beam, when they diverge, will still match the divergence of the grid that you utilize. So that's how they determine the focal range of a focused grid. Okay. Now, again, I told you that all of this information about a grid, like when it's constructed, it literally would be on a label on the grid, and it would tell you things like what the grid ratio is, what the inner space material is made of, what's the grid frequency, what size is the overall grid, is it a 14 by 17 grid? It would also tell you the materials that are used in the construction, like the inner space material, the lead material. It would determine all of that. So it would tell you the materials that are used in construction, and if it was a focused grid, it would also tell you the focal range that was available. So when we use that on the wall bucky and the table bucky, you want to make sure that all of those things, that you're aware of those. It also comes into play when we use those on portables. We would have to know also what grid ratio it is, what the grid focus is, what the focal range is, what the materials are made of, so that you would know which grid you would want to utilize. So all that information is actually found on a label on the grid itself. Okay. So again, just to kind of reiterate, we have focused grids and we have non-focused or parallel grids. And then we have linear grids. So most of the grids that we use in the field are linear focused grids. And then they have specific focal ranges where it says that we have to be within a certain SID range in order for that to work. All right. And if you're outside the focal range, we'll talk about in a little bit, you actually can exhibit what's called grid cutoff. Now, the grids can either be stationary or they can be moving grids. These examples here, these 3 examples of a wafer grid, a grid cassette, and a grid cap, these are all stationary, non-moving grids. Right? So these would be things that you would take and utilize either on portables or in the department. You might use these where you have a wafer grid, which basically your wafer grid matches the size of the image receptor that you're using, and you literally place it on top of the IR. Okay, the wafer grid literally just sits on top. You typically have to tape it to the surface of the IR. It's just literally a flat piece of aluminum that contains the lead lines in there, and you put it on top of your image receptor, you tape it to the surface, and that is a wafer grid. Those used to be used quite a bit, probably not as much anymore. We also used to use what were called grid cassettes, where it literally was an image receptor that had a grid permanently mounted to the front surface. And this was typically utilized with film, because you would place the film in the image receptor, and it was very heavy because it also had the grid attached to it. So it was one unit. It had the film in there, and it was a grid that held the film all in one unit, and you would place that underneath the patient to use. Again, probably a little more old school. The things that we tend to use now most often are called the grid cap, and that is a permanently mounted grid, and what it allows is for the IR to slide in behind it. It's almost like a sleeve for the IR, and that is called a grid cap, kind of like a cell phone case. Your cell phone kind of slides into the case. That's what a grid cap is similar to, and that is typically what is used in the field most commonly now, is a grid cap. So it also has a permanently mounted grid, but the image receptor is allowed to slide in behind that. And again, these three examples are examples of stationary, non-moving grids. Okay. Now, a reciprocating grid is one that moves. So when the grid is stationary, like those ones that we just mentioned, the grid cap, the grid cassette, and the wafer grid, the problem with those is when the grid is stationary, it is possible to see the grid lines on the radiographic image. That's what happened when Gustav Bucke came up with that. They were able to see the grid lines on the final image. So Hollis Potter came along in 1920 and recognized that if he removed one set of strips, making it a linear grid, and he added motion to it, then he could blur out the grid lines that were seen on the image. So Potter came along, he added motion to it, and now technically what this should be called is a Potter-Bucke diaphragm, because Potter improved on Bucke's original design. So the Potter-Bucke diaphragm is typically located below the radiographic tabletop and above the tray that holds the image receptor, because remember, it's beyond the patient, but in front of or above the image receptor. So what happens is you have grid motion that's controlled by the X-ray exposure switch, so that when you start to make the exposure, what happens is that starts to move that grid and blurs out the grid lines, and it moves back and forth in a lateral direction over the image receptor during the entire exposure. It actually starts to move during the rotor phase of the switch, when the anode starts to spin and the cathode starts to heat to release the electrons. The grid starts to move, and it moves continuously until the exposure is done. And by doing so, it blurs out the grid lines so that they are not visible on your final image. All right, this next slide is, I don't know what happened, so I apologize with that. You can probably see in your PowerPoint it's a little bit more clear, but this is talking about the grid conversion factor and how it's a mathematical expression of the mass with a grid divided by the mass without a grid. Okay, and this formula we've discussed before. This is on page 163, and ideally it tells you when you're changing from either one grid ratio to another, or you're going from no grid to a grid ratio, it tells you how you can calculate the mass change that needs to be used to compensate for the difference in grid ratio. And the formula, you can see that relatively clearly, is the grid conversion factor, the second grid conversion factor, divided by the first grid conversion factor times your mass. So on page 163, it shows you the grid ratio where you have no grid would be a grid conversion factor of 1, and then a 5-to-1 is a 2, 6-to-1 grid ratio is a 3, 8-to-1 is a 4, 12-to-1 is a 5, and a 16:1 is a 6. So you could take the conversion factor of whatever grid you're using, and you could divide that into the grid ratio that you're going to use and multiply it by your mass to tell you how to make the adjustment. Because if you're going to a higher grid ratio, you need more mass because you're going to pull out more quantity of photons and you have to compensate for that loss. If you're going to a lower grid ratio, you would end up using less mass because you're going to have more inner space, more photons will get through, which means that you can use less overall quantity of photons. And again, I apologize for the blurriness of that slide. Ideally, in your printed PowerPoint, it is not blurry, and you can see exactly what I'm talking about. All right, grid cutoff. What is that? That is not a good thing. When you get cut off in traffic, it's not a good thing. When you exhibit grid cutoff, it is also not a good thing. So grid cutoff is where there is a decrease in the number of transmitted photons that actually reach your IR because of some misalignment of the grid. Typically, this is a technologist has caused this error. Okay, so there's 4 types of grid errors. There is called an upside down focused grid error, an off level grid error, an off center grid error, and an off focus grid error. So when we look at these, the first one, the easiest one to detect, is an upside down focused grid error. This happens when you have a focused grid, and remember those lead lines match the divergence of the beam. If you were to place that grid upside down on the image receptor, the grid lines would go against the divergence of the beam. So what you would have is pretty much exposure in the center, and then as you get further to the outside, it would absorb those photons because they would not match the divergence of the beam. They would actually be the opposite of the divergence of the beam. Now, this is very hard to do because there's typically a label on the correct side and you place that label up. So not saying that this could never happen, but it'd be very hard to do that. I could see maybe a student making that error, but typically a technologist is going to recognize that the grid is upside down and correct that before they make the exposure. But if they didn't, this is what would result. An off-level grid error basically is when the X-ray beam is angled across the lead lines. So when your grid is not level and not when your lead strip is not level and not your central ray and your photons are not perpendicular to your IR, that is what happens. Now, how does this occur? Typically, this can occur on portables when the weight is not distributed evenly across your image receptor and your grid. This is actually one of the most common grid errors. Okay, it's the most common type of grid cutoff, and either your tube or your grid is angled. All right, and this always typically happens with portable X-rays. And what you end up with is a loss of exposure on the entire image receptor. So when they show you this grid cutoff, picture A represents proper alignment, picture B represents that it's off level. It's not properly aligned. So even though it's digital and the brightness attempts to appear correct, the quality of this image is much poorer compared to picture A. So this would be picture A, this would be represented by picture B. So off-level grid error is the most common type of grid error that we see, typically with portables. Off-center occurs when the central ray is not aligned from side to side with the center of a focused grid. Okay, typically this happens when you're not in detent, D-E-T-E-N-T. that is something that will have to be shown to you as far as detent. But usually when you have an off-center grid error, it means that your tube is not in detent, because your central ray would not be aligned with the center of a focused grid, which means that the divergence would no longer match, and you would end up with grid cutoff across the entire image, because now the divergence isn't matched because you're not centered to the center of the grid. All right, so an off-center grid error. Typically their name implies exactly what's going on. Like an upside down focused grid, you place the focused grid upside down. Off level, the grid and the central ray are not level to each other. Off center, again, your central ray and your grid is not centered to each other. An off-focus grid error, this occurs when you use an SID that is outside the recommended focal range. Okay, we said that the focal range is determined by the convergent point or the convergent line, and if you are outside the recommended focal range, then you will exhibit an off-focus grid error, again, because the divergence of the beam will not match, and you will exhibit grid cutoff. Typically, it will occur if the SID is less than or greater than the focal range. So if your focal range was 40 to 52 inches and you used it less than 40 or greater than 52, you would exhibit an off-focus grid error. Okay, so there's a loss of exposure on the edges of the image where it does not match the divergence of the beam, whether you're below the focal range or above the focal range, both would exhibit the same exact way. So that is an off-focus grid error when you're outside the focal range. Another error that we can see, especially with digital imaging, is called the Moore effect. Okay, the Moore effect is a zebra pattern. It displays like zebra pattern on the image, and that comes about when you use a stationary grid with CR imaging. So you're using CR, which is a form of digital, and you use a stationary grid. Typically what will happen is the grid frequency is similar to the laser scanning frequency when it's being processed, so this zebra pattern results. And this is actually quite a common error that we've seen now with our digital imaging, giving you that zebra pattern. And there's really no way to correct that other than to re-expose the patient. So kind of a frustrating grid error. As far as using a grid, recognize that grids are not appropriate for all exams. Grids are not appropriate for extremity exams. Remember, if the part is not thicker than 10 centimeters or 4 inches, or your KVP is not above 60, there is no reason to utilize a grid. So when you're deciding to use a grid or selecting the type of grid to use, you have to consider how good is the contrast improvement going to be, what is the patient dose going to be, and what's the likelihood of having grid cutoff if I am utilizing a grid. Realize too that we've also mentioned, it's not in the book, but I have mentioned to you that there is currently software available that is virtual grids, meaning that you're not having to raise the actual exposure, you're not having to raise the mass value to the patient to utilize a real grid, but there is software that virtually uses a grid where the program is designed to remove those low exposure pixel values from the histogram analysis, so it presents your image as if you used a grid, but you're not having to manipulate the exposure factor and raise your exposure to the patient, but you still get the same advantage of it looking like you utilized a grid. And that is becoming more and more popular. As far as radiation protection, again, we always want to limit the size of our X-ray field to our area of interest, because that will decrease the scatter that is produced in the patient, and ultimately that will reduce the amount of exposure to our IR. Okay, so when we limit the field size, we limit how much scatter is produced, and anytime you reduce the amount that is produced in the patient, you're going to limit how much is actually striking your image receptor. When you collimate to the area of interest, it's an important radiation safety practice. It helps adhere to the ALARA principle, and that should be something that we routinely do. You should always collimate only to the area of interest or just beyond. And if you limit the use of a grid or you use a grid with a lower grid ratio, that will actually decrease the amount of dose that you are giving to your patient, which is also a good thing. So you always want to use the lowest grid ratio that will provide you the contrast improvement without over-radiating your patient. The air gap technique is another way to limit scatter reaching the IR. This image is actually found on page 168, and it's just another way to limit the scatter that reaches the IR, because you purposely increase the OID, which is the distance between the object you're imaging and your image receptor. And what that does, remember that when the scatter leaves the patient, it still has the potential, it's changed direction. So if you increase the OID, it allows scatter to miss your image receptor, which would also improve your contrast. This is not something we utilize often, but it is an option. If you had no other option, you could still utilize the air gap technique. Last, they do show you that you can use shielding accessories, meaning that you could place a lead strip behind the patient. In this image, I'm going to assume that they're imaging the lumbar spine. And because there is a lot of scatter created in the abdomen, especially the spine of a patient because of the thickness and the radiopaque material in there, like your spine and the pelvis and things like that, if you were to place a lead shield behind the patient on the X-ray table, it would absorb some of the scatter radiation created and not allow it to strike your image receptor. Okay, so this is just another way to help limit scatter that's produced in the patient from reaching your IR. They also tell you anytime an individual is in the X-ray room during an exposure, they should always be wearing a lead apron. Whether it's you, the radiologist, one of the patient's family members, they should always be protected against that scatter radiation that can come from the patient, because remember, this is our biggest source of occupational exposure. So you always want to try and make sure that anyone left in the room is wearing lead to protect themselves from that scatter being released from the patient. All right, and that concludes the chapter on scatter control. If you have any questions or comments or concerns, I hope that you wrote those down and you'll bring them to my attention the next time we meet, and hopefully I can help clear up anything that's confusing or that doesn't make sense before we move on. Thank you so much.